Hey, this is Nick Marchuk recording a video for ME433 Advanced Mechatronics at Northwestern University in 2022. In this video, I'm going to talk about using the MPU6050 Inertial Measurement Unit, or IMU, sensor that happens to talk I2c. In the last class, we talked about using I2c to talk to an I/O expander chip. In this video, I'm going to show you how to use a slightly more complicated chip. It's a sensor, and it measures acceleration and gyroscopic motion. So let's start with looking at the actual chip. This is manufactured by, apparently, this company STEM-EDU or STEM-EDU. So that's the breakout board, and the main chip on this breakout board is in the center. That's the MPU6050, manufactured by a company called Invensense. This is actually kind of an old chip, probably released around 7 years ago. At the time when it was released, it was a big splash because it was very inexpensive and very sensitive for what it does, and a very good deal. Today, its specs aren't really all too impressive, but the price is still very low. I'm almost suspicious that this is like a knockoff chip or something, because we can get 5 for $13. Just very, very low price. So hopefully they'll work. The few that I've tested have worked fine. But when we look at this breakout board, we can see it's got some resistors and capacitors. It's actually got a little LED at the bottom to indicate that it has power. I think it has a voltage regulator there, so that we could power this with 5 volts if we didn't have 3.3 volts available. They actually give us a circuit diagram, which is nice, right here on the Amazon page, which is not like most Amazon products. So we can actually see the LDO that takes 5 volts in and makes 3.3 volts out. You can also give it 3.3 volts as an in, and it still makes 3.3 as an output, so you don't have to power this with 5. We can see how they've wired up the MPU6050. They have pull-up resistors on the SDA and SCL I2c pins, so we don't have to add those externally. Those are built onto our board already. And then hopefully they put all the right capacitors in the right spots, depending on what the spec sheet says. And what else can we see? There's an address pin called AD0, pin 9, which apparently is not hooked up to anything. So hopefully that's not a mistake, that they don't have to add a pull-up or pull-down resistor or something. Yeah, so basically, oh, no, actually, look here at the bottom at the J1 con, it shows AD0 has a pull-down resistor of 4.7K. So the address pin has been made a 0. So likely this has an I2c address with one address bit that we can change. So you could have 2 of these on the same I2c bus by having one of them have an AD0 pin hooked high and the other one with this pull-down resistor low. So we won't pull it high or anything, we'll just let it be low. We'll just have to remember when we make our I2c address that the AD0 bit is 0. First maybe let's talk about the accelerometer and the gyroscope that's inside of this chip. So this is the datasheet provided by Invensense, which is slightly strange in that they provide 2 PDFs for this chip. They have this datasheet as well as another one called the register map. So if you read through the datasheet, it tells you all the specs of how this chip kind of works and the theory behind it, but it doesn't go into the details of what are the registers and what bits do you have to set inside the registers to make the chip work. That's in this other datasheet, the register map. So I guess some manufacturers do that. This is a 6-axis motion tracking device, if you would like to think of an inertial measurement unit of doing that thing. It has a 3-axis gyroscope. So a gyroscope measures angular velocity around the X and Y and Z origin of this chip. And it has a 3-axis accelerometer, so that's measuring the acceleration of the chip. So if we were to just look at the raw data coming out of this chip, we would expect, when it's not moving, the gyroscope data to be 0, because if you're not moving, you're not rotating, the value should be 0. The accelerometer, though, the output of that is going to be measured in how many G's of acceleration is the chip undergoing at any given moment. So if you think of the chip as XYZ, where X and Y are parallel to the ground, and then Z is perpendicular to the ground, the acceleration in X and Y should be 0 if you're not moving. And then Z should be giving us 1 G of acceleration. So one complication of using an accelerometer is that you're always under 1g if you're just sitting on the ground. If you're in free fall, okay, now you're moving with acceleration. So that's different. And then when you're moving, so let's say I move from point A to point B, I have to accelerate to get up to some velocity to get to that position. And then I have to decelerate to stop at a new position. When I look at those accelerations, possibly the acceleration from gravity that I'm going under is actually much bigger than the acceleration I'm applying to the chip to make it move in a different position. So interpreting the data that comes out of the accelerometer could be a little difficult because of this confounding factor that we're always accelerating under gravity. Whereas the gyroscope does not have that effect. The gyroscope only tells you if you're rotating about the center of the chip. So it should technically say 0 when you're not moving. So most IMU sensors give you that raw data. What's kind of unique about this chip is that it has a digital motion processor inside, which we're not going to use, but basically that means there's a microcontroller in here that can read this data and then do some algorithms on it to turn it into more interesting, useful data. Like, for instance, you probably want to know what your position is at all time. This chip doesn't measure your position, it measures your angular velocity and your acceleration. So if you were to integrate that information, you could probably get your position. Turns out that's very hard, so usually you don't do it. But that's the idea behind this digital motion processor inside of the chip. It's trying to, what they do is like sensor fusion, or here there's their trademarked motion fusion, whatever that means, algorithm. And a lot of times that algorithm also needs more data. So for example, you can add an external 3-axis compass chip, which is a magnetometer. That could tell you heading. It would tell you like what direction is north at any given time. Once you know which way is north, you also know which way is down. If you know which way is down, then you can use that information to subtract off the gravity vector from your 3-axis accelerometer, and then things kind of get easier. But magnetometers don't really work when you're surrounded by noisy electrical signals or a big metal cage like inside of a building. So anyway, that's part of the what they're selling this chip for, saying that we've got some processor in here, but usually don't care. Usually all you're saying is, I would like the raw gyroscope and accelerometer data, and that's how we will use this chip. So most sensors use I2c for communication. There's another version of this chip, the MPU6000 instead of 6050, which can talk SPI. Either way, all the data that comes out of this chip is 16-bit. So numbers that are represented by 2 to the 16, which is 65535 different possible values. And the values will be signed because you could be going negative acceleration or positive acceleration. And then that number that it's reading has a different set of scales. So we can set this sensitivity to plus or minus 2G, or if we think we'll be undergoing higher Gs, plus or minus 4G, 8G, or 16G. So if we set the sensitivity to plus or minus 2G, we'll have very fine resolution of how many Gs we're undergoing. But if we accelerate very quickly, this will rail at plus or minus 2G. So we might be undergoing more than 2G if this says we're going under 2G. So then you could say work at plus or minus 16G. You'll have lower resolution of the Gs, but you'll be able to read more Gs. So I don't know, if you're going to go into a rocket ship, maybe you want 16 Gs. If you're going to be a cell phone, you probably want plus or minus 2G because people usually don't move at higher Gs. The gyroscopic sensitivity plus or minus 250 degrees per second. So if you're going to be doing 1 revolution per second, this would not be sensitive enough. Up to 2000 degrees per second. And so there's plus and minus. Obviously, you can choose a high sensitivity, but you have to make sure you don't go so fast, or a low sensitivity, and then you can go faster. Okay, another feature of this chip is that it has a 1024 byte FIFO. So one thing about these kinds of chips is that it's very expensive electrically to stay on all the time. So if you wanted to read data from this chip 100 times a second, and you left your microcontroller on all the time and delayed by 0.01 seconds to get your 100 hertz update rate, you're leaving microcontroller on for a long time, and it's using a lot of power. So it'd be helpful to actually ask the accelerometer, hey, why don't you sample yourself until you fill up this FIFO? When you're done filling yourself up, wake me up, I'll grab the data, process it, and then I'll go back to sleep. And so the ability to have the microcontroller go to sleep and put some of the effort onto your sensors, which are lower power, can be very useful on a battery powered system, say like a Fitbit, where you're trying to count steps, you don't necessarily need to count the steps in super real time. So you can tell this accelerometer, hey, take 10 seconds worth of data for me, wake me up, I'll take those 10 seconds of data, I'll calculate how many steps there were, and then go back to sleep. So that's why there's memory on this chip. The interesting thing about these accelerometer gyros IMUs is that they are really made possible by MEMS technology. So that's micro electromechanical systems. MEMS is the ability to take the technology that makes integrated circuits, where you essentially use laser light pointed through a focal lens to burn off photoresist on silicon wafers to make geometry, and that geometry turns into things like transistors on the chips. You can actually use that technology to burn things into the chips that are not electrical. You could make mechanical systems like little tiny gears. They make gears that are 1 micrometer in diameter and crazy stuff like that. So the ability to make little tiny silicon mechanical parts that then you can weave into electrical parts is what MEMS systems are. So, for instance, the accelerometer of these MEMS chips means that they make a little tiny mass on a spring damper system inside of the chip. And that mass on a spring means that when you flip the chip over, the mass gets pulled in the other direction, the springs bend the other way. And if you could measure the position of that heavy silicon mass on these little tiny springs inside of the chip, you can measure the force applied to this mass by measuring the displacement of the springs, if you know the spring constant. And you could do that with some kind of like capacitive sensing to sense distance. So inside of these chips are little tiny mechanical systems that are being read electrically to figure out the acceleration. And the gyroscope's a little bit more complicated. There's like a resonant rotational spring involved there, so it's kind of more complicated. But it's kind of cool. These devices are made possible by the same technology that makes little tiny transistors. Very different than, say, 50 years ago. 50 years ago, when you're launching a rocket into space and you need an IMU to read the acceleration and the gyroscopic motion of your rocket, you had these really big, heavy mechanical motor-based systems costing millions of dollars. And our cell phone revolution that said, hey, when I turn my cell phone 90 degrees, I'd like to know so I can flip my screen, forced the manufacturers to figure out how to make accelerometers very inexpensive and still very accurate. And we see the benefits now of being able to buy these kinds of breakout boards with accelerometers in them for only a few dollars each. Okay, so that's a little bit of the history of accelerometers and gyroscopes. And so this particular chip we're going to be using the 6050 I2c version. So we need to make connections to SDA, SCL, power, and ground. There's also this AD0 pin that helps us set an address for the chip. It has a pull-down resistor, so we'll just know that it's grounded. So actually very easy to connect this chip to the PIC. All you have to do is connect SDA to SDA, SCL to SCL, power and ground to power and ground. We don't need pull-up resistors on the SDA and SCL because they're built onto the breakout board. So very easy to connect this chip to the microcontroller. So with any I2C chip, the main question is going to be, how do we talk to it? What do we have to ask it to do to get the data out? And once we get that data out, how do we manipulate it to see it? So that's the goal of some sample code that I've pre-written for you. And normally I wouldn't go as far as I have to give you all the code that just makes this chip work. But in lecture, we're going to have a guest lecturer, Dan Lynch, who is going to show you different methods of taking the data, the raw data out of this chip and making it more interesting, trying to get, say, position data out of acceleration. So we're not going to waste time figuring out how to get the raw data out. I'm going to give that to you, and once you have access to that raw data, now you can do something interesting with it. So how about I do a demo first, and then we'll go back and look at the I2C code that's necessary to talk to this chip and get the data out. So I've got my PIC code up, and I have code, and this is all from, I should say, from Dan Lynch, and I've made a few modifications, but we have an init function that turns on the MPU6050 with the appropriate sensitivities of plus and minus 2G on acceleration, and I think plus or minus 2,000 degrees per second on the gyroscope. So this turns on I2c. This talks to the chip to set up sensitivities. The next thing we're going to do is we're going to ask the chip, hey, what's your name? And if it replies with the correct result, we will know that the chip is plugged in and ready to go. Kind of already done that because it wouldn't respond to this if we didn't do this already. But that's just a good check to make sure the I2c communication is working. If that is the correct name of the chip, we'll go on. And in this particular example, I have UART going. So I'm going to call my read UART function, which is a blocking function. The code gets stuck here forever until it sees a new line come from my keyboard. So on my computer, I'm going to hit the enter key, and the PIC is going to then move on. It actually doesn't use the fact that I typed any data, just cares the fact that I sent a new line. Once it has a new line, it's going to collect this num data points. So right now I have this 300 data points at 100 hertz. It's going to save those into some arrays, and then after it's collected, so 300 data points at 100 hertz, it'll take 3 seconds worth of data. After it's collected that data and saved them into arrays, then it goes into a for loop that prints all of the data back to the computer. So what is this data? We have the acceleration in x, y, and z. We have the gyroscope, so the angular velocity about x, y, and z. And then this chip also knows the temperature of the chip because it uses that to correct for some nonlinearities. So I'm going to print that out in this format. I'm going to print out an index, and then the acceleration, and then the gyro, and then the temperature. So one line of text for one data point containing all these different pieces of information. So there's going to be 300 lines of these that pop out. I've already loaded this onto my PIC. So all I have to do is go into my terminal program like PuTTY or Screen, open up my COM port, and the PIC is just waiting right now for the enter press or the new line to be sent. So I will press enter, and after 3 seconds the PIC has collected all the data, and then probably takes a lot of time, like 3 more seconds, to send all the data. And what we can see here is the first number that comes out, it says 300. That's the index. So I count down from 300 to 1. So I'm kind of sending the data index backwards. And then I see my x acceleration, my y acceleration, my z acceleration, my x gyroscope degrees per second, my y and my z, and then the temperature in degrees Celsius. And each of these data points happened at 1/100th of a second. And so I could do this again if I enter, and now I'm going to grab my breadboard. I'm going to shake it back and forth. Let's take in data for 3 seconds. All the data comes out. Hard to see, right, that I'm shaking this thing. So this method of seeing the data in my terminal program in PuTTY or Screen is good to make sure everything's working and I'm seeing the right format and all that kind of stuff. But what I really would like is a computer program to grab this data and then plot it for me. So for that, we're going to use Python. So I'm going to close my terminal, and we're going to take a look at some Python code. And I'll do a brief description of what this is now, and we'll come back in a few minutes to examine it more in depth. So in this Python code that I'm running in Visual Studio Code, I have a .py file. This is provided to you in the Git repository. I'm importing the serial library so that I can talk to a serial device like my UART. And I'm saying open that serial port. Here's the name and the speed. And then I'm just printing it back to my console so I can verify that I opened the right one. And I've got some blank lists here where I will store the data. And I will have Python. So as soon as I run this Python code, it's going to print the new line character for me. And then it's going to sit in this loop and say, while that first number that comes back, which starts at 300, counts down to 1, while that's bigger than 1, let me read until I get a new line. So I'm going to get one line from the PIC. That one line is all these letters and numbers. I guess it's all numbers. And stores it as bytes. And so then I'm going to convert my bytes to a string. And then I'm going to convert my string into a list of floats. So I finally get the array of the data that I want. Then I'm just going to make sure that I have 8 data points, and I'm going to stick that data into my arrays. This will run until finally I get all 300 data points. Then I'm going to import matplotlib, which is my plotting library. I'm going to make a fake time array, and I'm just going to plot the XYZ acceleration versus each other, the XYZ gyroscope data versus each other, and then make one plot of the temperature. And then when I'm done, I'll close the port so I could run this again. So in Visual Studio Code, you can open up these terminal windows. Nice thing about doing that is that it opens your terminal in the right folder, so you don't have to like navigate to that folder. And I can call my program by saying Python IMU.py. So it has opened up com5. It sent that /n that collects the data, sends the request for data. The data comes back, is collected. Now it's being plotted very slowly. So here's my acceleration data, and the chip is sitting horizontally on my table right now, and I'm seeing two of the axes, x and y, about 0g. And then my z acceleration should be coming back as 1g because I'm moving right now. So some kind of offset here, but constant, as we kind of expect. I'll close that, and then my next plot is generated. Here is my gyroscopic data, and XYZ gyroscope, constant because I wasn't moving, a little noisy, and also one has an offset. Pretty typical for the gyroscope to have a little bit of offset that depends on the acceleration data. So there's lots of interesting digital signal processing we could do here to get rid of this offset by using the data that came from the accelerometer to change the gyroscopic data and inform how the offset should change. Okay, so let's close that. And then here's our temperature data. Temperature is pretty constant, so it's basically bouncing around 23 degrees C. I actually, an American, I have no idea what that means. Okay, so let me do that again, but this time I'm going to start taking my board and I'm just going to move it up and down on my table, so parallel to the Earth, going back and forth like 2 hertz. I enter to collect the data while I'm moving it at 2 hertz. After 3 seconds, I can stop moving it because it's collected all the data, sent it back, Python's processing it, and trying to plot it. And so we can see the z acceleration still 1g because I'm not moving up and down, I'm moving parallel to the Earth. And then the blue must be my, see, I was moving it according to the PCB in the direction of, I guess that's x, and then y might be subtly changing it. So we can see those rotations there. We also see some kind of like, at that peak, some kind of interesting waveform there. Maybe some stick slip as I change my acceleration from one direction to the other. I wasn't really rotating about any particular axis, so my degrees per second should still be about 0. So it's saying 4 degrees per second is basically 0. And I didn't touch the chip, so the temperature is pretty flat. Let's do it again. This time I'll rotate about the center of the chip. So I'm not really accelerating, but I'm rotating, so the gyroscope should give me some data. Rotate, rotate, rotate. Okay, should have sent the data. Now it's plotting. So a little bit of acceleration just because I'm jiggling, but not a lot compared to 1G. And there's my gyroscope. I was rotating about Z, and that's a pretty good sine wave as I was rotating. And then temperature's flat. So the last thing I'll do is I'll run the code again, and at this point, as soon as I hit enter, I will touch the chip, and hopefully me touching the chip raises temperature. So touch. Okay, should be 3 seconds. So there was no motion. That little bump right there might be the fact that I touched it. Shouldn't really have rotated. And then there's the temperature rises. I touched the chip and the heat from my finger warmed the chip up. Lots of interesting stuff here, and hopefully Dan in lecture will talk about different attempts at filtering and using this data. But I'll point out, for instance, this is real world data, so you don't expect real world data to be nice and smooth. Every time you read the signal, you get a slightly different result. So a good low pass filter here would be in order to smooth it out. But sometimes you don't want to go too low on that low pass filter because you might get rid of some interesting effects. So let's jump back to the PIC code. I've given you in the Git repository this main.c, which is kind of your example of how to use this chip, as well as MPU6050.c and h. So let's start with main. This is your basic template, and we've added our I2c library, and then we've added an MPU6050 library. This library is going to call functions in the I2c library so that the specific ability of the MPU to be talking over I2c uses the basic low-level I2c commands. And then I've been kind of lazy to stuff my UART stuff here instead of in its own library. So we're going to call the init function, and we can call a whoami function that returns one char, which is the value hex 68 if we're talking to the right chip. And let's look at these like high-level functions. We have a burst read MPU6050, and we're telling that function, here is an array of chars. So take the data that you get from this I2c communication and put it into these chars. The data that comes out of the chip is 16-bit, and the char is 8-bit. So that must mean that the data that's coming out has to be processed after it comes out. And it has to be processed in two ways. We have to take the chars and recombine them to make shorts to get the 16-bit data. And then we have to take those shorts and we have to use the fact that we set the sensitivities to certain values to figure out what the G's are. So this burst read function gets all the data out of the chip, but it's not processed yet. And then this these convert functions takes the data out of that array and turns it into 16-bit, and then turns those into their floating point numbers. And so I have these floating point arrays to store the data into. So relatively straightforward. Once you have this library going, you have to call the initialization function. And then you have to call the burst read and put the data into an array, and then call functions to take the data out of the arrays. So let's look at all the functions in this library. Dan was very nice to make this library for us, and he even linked to the datasheet and the register map so that you can figure out what else this chip is capable of doing that we don't have functions for yet. There's lots of other cool functions that it can do that we just have the very basic stuff, how to get the data out. So here's the address for our chip, based on the fact that the AD0 pin has a pull-down resistor. So the I2c 7-bit address is hex 68. So sometimes we write the binary version of our addresses, and sometimes we put it in hex because it's very easy to mistype ones and zeros in binary, harder to mistype the two characters in hex. And then the data that we're getting out of this chip is acceleration and gyro in XYZ, so that's 6 pieces of information, plus temperature, so 7 pieces of information. Those are 16-bit datas, and I2c is always an 8-bit communication, so we must need to do 14 pieces of data, 14 chars to get the 7 16-bit numbers we're interested in. Okay, and of course, we don't need to get all that data out. So in the future, if you're like, oh, I really don't want the acceleration data, I don't need the temperature or the gyro data, you could make this number 6 instead of 14. So inside of I2c chips, there are registers that we would like to either change the settings of the chip or read from to get the data out. So here are some of the important registers. A config register, which is like the general purpose config for the chip. Then specifically configs for the gyroscope and the accelerometer, so like the sensitivities involved. And then some power stuff. The chip when it first turns on is asleep, so you have to wake it up. And you could probably turn the accelerometer and the gyro off independently to save more power, those kinds of things. We'll go take a look at the register map in the future to see how many configs are there, because maybe there are more that are interesting we're not using here. Then here are the registers for the actual data itself. So the acceleration data starts at X at register 3B, and then the next register 3C is the low 8 bits of the 16-bit data. So the X low and X high 8-bit numbers concatenated together make a 16-bit number. That's the acceleration X data. So 3B and 3C. 3D and 3E are the acceleration in Y, and then F and 40 are Z. So we can see that a sequential read of the registers starting at 3B and then just going through all the registers gets all this data out of this chip. So very convenient that all of the interesting registers are right next to each other. except for who am I, which is a little bit further down, but we only need to read that once. So we're going to have an init function, a function that asks for the who am I register. This burst read function, kind of complicated because we're going to send it the pointer to an array of chars to get all of the data at these register values. Then we're going to have functions that get the acceleration 16-bit data out of the array, and then another function that calls that function that takes that 16-bit data and converts it to a floating point number based on the sensitivity. And we have conversions for all of the different types. And then low-level functions, if you wanted to read 1 byte from I2c, so that's the 5-step process in I2c of starting and then writing the chip address, the register, the value, and then stop it. That's what this function is going to call, knowing the register we're trying to change and the value. Sorry, the address of the chip and the register we want to read from, and then it sends back 1 byte. And then the burst read, which takes the address of the chip, the register you're going to read from, the array you're saving the data into, and then the number of data points in that array. So this is the sequential read function that we're taking advantage of for this chip. And then a write byte, so that's the simple what's the address, what's the register, what's the data you want to put at that register. So we can look at the C code source. So our init MPU6050 function calls the I2c Master Setup function, so that just turns on our I2c. Then we're calling the write a byte function that says we now have to initialize the chip. So at this address, which is the address of our chip, into the power management control config register, we're going to write the number 0. So that turns the chip on. Then we're going to write to the acceleration configuration with this number, which at the datasheet says will give us the plus minus 2G sensitivity. Then we do a similar thing for the gyro to get that sensitivity. Then we have the function that reads who am I. We have the burst read function, which is just calling the burst read I2c function, which I think is down here. Okay, so here's reading 1 byte, which we've covered in the previous chip. Here's our burst read function. So the burst read function is interesting because it's trying to return many bytes of data, but in C you can't return more than one piece of information, one variable. You can only return one thing. So here we're going to be a type void. We're not going to return anything. Instead, we're going to send a pointer to an array, and then because we have the pointer, we can directly manipulate the contents of that pointer from this function. So we don't have to return anything. We're actually just editing the variable. So a burst read, we're going to send our start bit. We're going to send the address with the write bit. We're going to say, here's the register I would like to read from. We're going to do a restart. We're going to send the address with the read bit, so the chip knows we're trying to read from it. Then we're going to call our read function, and we're going to acknowledge with a 0 that says, okay, I acknowledge that I got the data from you. I'd like to do it again. And I'll keep doing it over and over until eventually I get to my very last data point, and then I'll act with a 1 that says, okay, now I'm done talking to you. And then I can do my stop, and the data is going into the pointer that I sent. So that's how we get multiple values outside of the chip without calling this read 1 byte over and over again. That would be kind of inefficient. This is a more efficient way to get lots of data out of the chip. So we've got the data out of the chip. It's in an array of 14 values of chars. So we need to take those chars and take the consecutive ones, put them next to each other, and concatenate into a signed 16-bit number. So these functions are returning a signed 16-bit number, and they're hard-coded to know that the X acceleration data is the first 2 bytes in the array, and the Y acceleration data is the next 2 bytes, and so on. So we take the first byte that comes out, that's the high byte, so we have to shift it left by 8, and then we OR it with the low byte to get a 16-bit number. Now that we have that 16-bit number, we need to take that signed number, which in this case for plus or minus 2G, for plus or minus 1G would be the numbers plus or minus 16,000. So we need to scale plus or minus 16,000 to plus or minus 1G. And that I guess that's this according to Dan. So nothing for you to do here other than trying to get my code to work. And so if you can stream the data out first, stream it to PuTTY and screen, then try to get the Python code to work. Now Dan's going to tell you about how to take that data and make more interesting things with it. Another option would be to take a look at this chip and see what we didn't have it do in this basic code. So if you look at this register map, we could see that there are registers 13 to 16 self-test registers. So we could put this chip into self-test mode where it can essentially test to make sure it's not broken. It kind of rings the X and Y and Z acceleration, and you can see that it rings to know that it's not broken. We can take a look at the gyroscope configuration to see what else is in this gyroscope that we didn't set. We set the sensitivity, the scale. There are other bits in here that maybe if you change them can filter or do something like that. What else do we have in this chip? External sensor data. So this chip has this internal processor that can do sensor fusion algorithms. It can't do that without an external magnetometer. This chip doesn't have a magnetometer inside of it. A more modern chip actually does come with an internal magnetometer, but if you had an external magnetometer that talked to I2c, this chip could actually talk to that chip. It could be the host and the magnetometer would be the device, and it could read the data from those chips and then use that in its own internal processor. Okay, probably more complicated that we need to get to. So I guess the final thing would be, let's look at this Python code to figure out how the data that I'm sending out gets read into Python. The big challenge is always just that C and Python deal with, let's call it character arrays, strings of data, a little differently. So if you don't use Python, you have to install Python. I prefer not using Anaconda or any of these Python installers. I just straight up install Python by itself, and then I straight up install pip, which is the Python package installer. Using pip, you could then install PySerial and matplotlib. If you've never done Python before, don't worry about doing all this. I can show it to you later. But if you're familiar with Python, you probably already have Python, Serial, and matplotlib installed. They're pretty basic low-level stuff. So we're going to open our COM port. I'm on Windows, so my COM port number is like a COM5 or COM6 or COM and then a number. If you're on Linux or Mac, this is /dev/tty.usb serial or something like that. And just like always, we have to set the baud rate here in serial to make sure that the bits are read at the right speed. Python doesn't really have arrays, they call them lists. So here's a list called AX and it's blank. And if I want to add an element to that list, I use the append function. So AX.append this piece of data out of some other list. So I have my data read, which is a list of letters that we call bytes. We can take the string function and turn that list of bytes using the UTF standard into a string. So now it's one variable of type string with all the letters in it. So it's number, space number, space number. And what I would like to do is split that string at the spaces, and then between the spaces, that string turn into a float. So this is a very shorthand Python method of kind of automatically doing that, kind of like a for loop. So now my data variable is a list with 8 things in it. The first thing being the index of the data point, and then x, y, z acceleration, x, y, z gyro, and temperature. I checked to make sure there's 8 just in case there's some kind of weird serial bug that I lost some data points because I was talking to serial too fast or something. Once I've got that data, I use the range function to make a list of numbers in the variable t that just goes 1, 2, 3, 4, 5 up to 300, the length of my acceleration. And then this matplotlib works a lot like plotting in MATLAB. So I want to plot t versus acceleration, red stars in a line, or blue stars in a line, or black stars in a line. So maybe I'll run it one more time. So I will call Python, and I want it to run my IMU.py function. As soon as I hit enter, it's going to collect the data. I'm going to kind of move my board in a circle. So we should see x and y acceleration in sinusoids, out of phase. Right there. And then I don't know what the gyro is going to do at that point. The z thinks that we're rotating a little bit, and the temperature should be relatively constant. So I think that's enough for this video. Have fun with that, and I will see you in the next class.